Hello, welcome to this lecture. Today, we are going to talk about some important theorems which form the basis of propositional logic theory. Let us start by looking the first one, Demorgan's theorem. We briefly discussed Demorgan's theorem in the first chapter of sets. Let us assume any two sets A and B. Then, De Morgan's first law states that the complement of A union B is equal to the complement of A intersection the complement of B. And for the second law, the complement of A intersection B is equal to the complement of A union the complement of B. Please note, the connectives and, or, and not, which are used in propositional logic, can be simply replaced by the set operations intersection, union, and complement respectively, and vice versa. Using this information, we can say that for two propositions P and Q, negation of P or Q is equivalent to negation of P and negation of Q. Also, negation of P and Q is equivalent to negation of P or negation of Q. Let us see the proof for the laws depicted by this theorem. To prove the first De Morgan's law, we must depict that negation of P and Q has the same truth values as negation of P or negation of Q. To match the truth values, we draw truth tables for each case. Let us start by drawing the table for negation of P and Q. Let's calculate the truth values of P and Q first. We saw earlier when we discussed connectives that only in the case where both of the propositions are true, the result is true. In all other cases where either of the proposition is false and leads to false. Now we will perform negation on each value. If it was true, it becomes false and vice versa. These are the final truth values for negation of P and Q. Now we will draw the truth table for negation of P or negation of Q. We start by calculating individual negations for each P and Q. Now using the OR operation, we perform disjunction, and as we saw earlier, only in the case where both propositions are false or results in a false. In all other cases where any of the propositions is true or results into true. That being said, we can plot the truth values for negation of P or negation of Q as shown in the table. And as we can see, both the truth values in the tables match, which means that negation of P and Q equals negation of P or negation of Q. Similarly, for the second law, we will draw the two truth tables, one for negation of P or Q and one for negation of P and negation of Q. For the first table, we start by calculating truth values of P or Q. As we saw earlier, in case of OR operation, the only case of false is the one where both propositions are false. In all other cases, the OR leads to true. Now, we perform the negation on these values. And this is the final table for negation of P or Q. Now on to the truth table for negation of P and negation of Q. We can write the negation values of P and for Q as we saw earlier. Now we perform the AND operation on these values to get the final truth table for negation of P and negation of Q. As we can see, both the tables represent same truth values, and we can say that negation of P or Q equals negation of P and negation of Q. We briefly discussed about contrapositive propositions in the ending of last lecture. Now we will see the proof behind it. Let us consider two propositions P and Q. The contrapositive of the conditional statement is formed by negating both terms and reversing the direction of inference. In order to prove the expression P implies Q equals negation of Q implies negation of P, we plot the truth tables for both the sides of the equality operator. Let us start with P implies Q. We know that only in the case where a hypothesis is true and a conclusion is false, the implication leads to a false. In all other cases, the implication leads to true. Now we will fill in the second truth table. Same as before, we can write the negation values of P and Q by flipping the truth values like this. Now, we will perform an implication between the negation of Q and negation of P values. This time, the hypothesis is negation of Q and the conclusion is negation of P. Only in the case where negation Q is true and negation P is false, the implication is false. For all other cases, the implication holds true value. Now, we can see both the table values match and thus the contrapositive theorem holds true. A single negation flips the value from true to false and vice versa. A double negation flips the flipped value back to the original value. The truth table for the double negation could be plotted in such a manner. Here we can see when P is true, negation P is false and double negation P is true again. Also, when P is false, negation P is true and double negation leads to false again. It is quite evident that P is equal to double negation of P. Let us see the implication theorem now. Implication is a disjunction of a negated hypothesis and the conclusion. Let us consider two propositions P and Q. The implication theorem states that P implies Q is equal to negation of P or Q. In order to prove the theorem, we compare the two truth tables. We have the truth table of P implies Q as we saw earlier. Again, only in the case where hypothesis is true and the conclusion is false that we say the implication is false, otherwise true. To form the second table, we fill in a column dedicated to negation of P. We now perform the OR operation between the values in negation of P and Q columns. The final columns in both the tables match and thus we can say that P implies Q equals negation of P or Q. If we negate an implication, we get a conjunction of hypothesis and negated conclusion. In terms of P and Q, where P and Q are two propositions, negation of P implies Q equals P and negation of Q. Now, we will draw the truth table for negation of P or negation of Q. The first table is an extension to the implication truth table. It further negates the truth values. To form the second table, we fill a column dedicated to negation of Q. We now perform the AND operation between the values in negation of Q and P columns. As we can see, the final values match. This means that the negation of an implication is equal to the conjunction of hypothesis and a negated conclusion. Or in simple words, negation of P implies Q equals P and negation of Q. Let us move on to the last theorem for today, the equivalence theorem. It states that P equivalence Q equals P implies Q and Q implies P. We have the truth table of P equivalent to Q as we saw earlier. Only in the cases where both P and Q are same, it results in true. When the truth values of P and Q are different, equivalence results into false. We can form the second table by extending the truth table for implication. We calculate the truth values of P implies Q and Q implies P, and then we apply the AND operator on the two implication columns. It is quite clear that both the tables match. This means P equivalence Q is equal to P implies Q and Q implies P, representing the if and only if function. That's it for today. We will revise the rules we gathered in understanding propositional logic in the next section before we proceed to predicate logic. Thanks for watching.